Hello all, welcome to this tutorials in which we will be looking at convolutional neural networks, its implementations, how do you obtain a pre-trained model, and how do you extract embeddings. Okay. Now these are the main features that we'll be looking at from the perspective of the implementation. So till now, I am assuming that all of you are quite comfortable with coming up with an MLP, implementing an MLP, and then running the training algorithm. So now we'll be going ahead with a regularized MLP, now wherein which now we have the idea of parameter sharing and then the local receptive fields, when you regularize them, now we get CNNs. Now from our theory sessions, now it would have been crystal clear by now. Okay, so now we will look at a very nice implementation, graphical implementation of CNNs. Okay, now this was done in Stanford CS231 Deep Learning for Computer Vision course. Now we are looking at its official website where we will go to this convolutional neural networks and then let's try to understand visually how does a CNN work. Okay, now this is an image. Okay, now the one that you are seeing here is an image, and these two are the two filters that are there. Okay, now each filter now will have some components, and that matches with the number of channels that are there in the input volume. Okay, here there are two filters, and each filter has three components depending on the number of input channels that are there. Okay, and then the kernel size, the filter size is 3 cross 3, and then as you can see here, how does it work? Okay, so it goes here. We will see the exact operation does this perform, but visually this is what it does. Now you can see here the green one moving, wherein which of post convolution operation, this is the outcome. Okay, now this is hovering over the different parts. Okay, so now let's go into I have taken a simple a still image of it so that we can understand how does this convolution operation work. So now, as you can see here, this part is only the image. The blue part which you see is the image, and then the zeros that you have put here, this is zero padding. Okay, now we have padded this whole thing with one layer of zero padding. So this is one. Now because now you have put one layer. If you want one more, you can put it here. Okay, and padding is used whenever you want to have some kind of a match in the output dimension. We will show it to you how. So now your input image that we have is 5 cross 5 cross 3. Okay, now for this convolution operation, so now the input that we have, now let's represent the input to this convolution operation as h in height, w in width into d in. Now this, in our current example that we are considering, this is 5 cross 5 cross 3. And please don't consider it post padding. Okay, now whenever we say image size, which is we are considering the pre-padding data, which is this. Okay, on this you are applying a 3 cross 3 filter. Okay, so now you have two filters. Now let's make that. So the number of filters in this specific example, so the number of filters which we represented by k. Okay, in this case, now please don't confuse this to number of classes that are there. Now here we mean k is the filter size. So sorry, number of filters. Now we have two. Okay, And then what is the size of that filter? That is the spatial extent of that filter, which is represented by f, which is 3. Okay, it's a 3 cross 3. Okay. So most of the cases we use a square filter size. Okay. Now it's not mandatory that you should use square filters. You can come up with rectangular filters as well. But in most of our computer vision applications, we will come up with a square filter. Okay. So now, and then you can see here, the movement is in each direction, it is moving by 2. Now it is here next, it moves by 2 units of distance. Now this is known as the stride. Okay. Now this is the stride, which is represented as s, and the value it is taking is 2. Okay. And then how much padding we have done? The padding is represented by P is given by 1. Okay. And any convolution is having these hyperparameters. Okay. So in a convolution layer, the values that these two matrices take, the filters take, okay, including the bias, no, these are the weights. Okay. These are learnt. No, I'm not saying about them. Now, what I'm saying is, no, the fixing of number of filters, the spatial extent or the size of the filter, the stride and the padding, these are hyperparameters. So you are not learning for any of them. You are fixing them and then proceeding. Okay. So now, whenever you have these hyperparameters and then the input size which is there, now we can actually predict the output size. So now, if you have any convolution operation which takes this h in cross w in cross d in. Now here w represents width, not the any parameters. Okay. Now when you apply a convolution operation, now convolution operation will have the parameters, the hyperparameters k, f, p, s with these hyperparameters. Now whenever we apply, now we get h out cross w out cross d out. And what will be the values of this? Now h out is equal to h in minus f plus 2p divided by s plus 1. Okay. And then width is w in minus f plus 2p divided by s plus 1. d out equals to k. Okay. Now just number of filters. So now let's put in these values and see whether there is a match. Now in our case, h in is 5 minus the spatial extent is 3 plus 2 divided by 2 plus 1. Now this is 3. Similarly, this is 5 minus 3 plus 2 divided by 2 plus 1. This is 3. This is 2. Therefore, now we have our output, which is h out cross w out cross d out, that is of size 3 cross 3 cross 2. Are we getting it? 3 cross 3, you have two such things. Okay, it's a 3 cross 3 cross 2. Okay. Now using these formulas, we can obtain with the given hyperparameters and the input dimension, we can obtain the output dimension. Okay. So now coming to the operation here. Now, how do we do it? Now, you have uh, you're actually currently looking at this part of the image using this filter. Okay. Now, what do? You perform element-wise multiplication of this matrix and this matrix. Similarly, you perform an element-wise multiplication of this matrix and this matrix. Similarly, with this and with this. Okay. And then you have a bias term, you add it out. Now let's do it. Now zeros normally we can always ignore. So I'm just marking these zeros so that just to know that where are zeros. I don't need to worry about those zeros. This is 0. So I don't need to worry about this. These two are zeros. I don't need to worry about this. The third one, this whole is 0. I don't need to worry about this. This is also 0. So I don't need to worry about any of these numbers while performing the operations, just for computational ease. I have a 2 here, minus 1 here. Okay, so now this is 2 into minus 1 plus, we have 2 here, minus 1 here, 2 into minus 1 plus, we have 1 here, plus 1. Now this is minus 2, minus 2, minus 4, this is minus 3. Okay, here you have 2 here, you have 1 here, 2 into 1 plus, you have 2 here, you have minus 1 here, plus 2 into minus 1 plus, you have 1 here, you have minus 1 here, you have 1 into minus 1, this is minus 1. Now coming to this, you have 2 here, you have minus 1 here, so this is minus 2. Therefore, the overall thing is minus 3, minus 1, minus 2. Now, these are from the element-wise multiplication. And then you have to add this bias term. In this case, the bias term is plus B1, which is 0. Therefore, the total is minus 6. As we can see here, you can see the minus 6 here. Okay. This is how. Now then you're looking at this point. Then you move by 2 units. You will go to here, these aspects, and then you will get this minus 1. Now and then once you are done here, now here you go to the next one. Here you take 3, 3 of this, 3 cross 3. Okay. Similarly, you perform. Now this is how you perform the convolution operation. Okay. So now this is just for your comfortability in terms of visualizations when you have a grid like structure. Okay. And then the next thing that we should look into is the idea of pooling. Okay. Now normally we have two kinds of pooling. One is max pooling, the other is average pooling. So now whenever you have a input, okay, now you fix a kernel size, okay, and then the stride. Now here I am saying that, okay, now this is 2 cross 2 is my filter, and then my stride is 2. Okay, so now I look at this, I take the maximum value, I obtain this, I take this, I obtain this, I take this and obtain this, I take this and obtain this. Okay. Now you get the maximum of them. That is what is known as a max pooling. If you take the average, now that is known as the average pooling. Now this size, now it's exactly the same formula you use. Now for example, if you look at that, now here the Hn is 4, minus F is 2, there is no padding, divided by 2 plus 1. This is 2. Correct. Now this is similarly you will do the other, so it will be 2 cross 2. Now always remember this. Now whenever we have a 2 cross 2 kernel and then the stride is 2, you are reducing the spatial dimension by half. That is what is exactly shown in this part of the figure. Okay. Now you have 224, 224, 64. When you apply a pooling, now with 2 cross 2 filter and then the stride of 2, it get reduced to 112, 112, 64. Okay, there is no change in the number of dimension, but there is a change in the spatial size. Okay, now this is max pooling. Now that we will be using whenever we need to reduce the dimension. This is the practical way of handling it. So now we come up with a network. Okay, and we say that it's a convolutional network which is used for classification. We are looking at the classification. You have a convolution operation in which there will be some filters and thing, and then after that you have a activation. Now, preferably, it is empirical again. So for a classification task, whenever we are dealing with images, okay, we use ReLU activation whenever we are dealing with images. Okay. So now you have the convolution, you have the ReLU, you have again convolution, ReLU, and then you have a pooling. Like this, you repeat, and finally, whatever you get as the final one, no, that you flatten it. Okay, you convert it into a vector, and then pass it through a fully connected layer to get whatever number of classes are there, whatever number of outputs are there. Now you try to obtain them. Okay, now this is the idea, full idea of the convolutional neural network. So, and see, always remember here there are 1, 2, 3, 4, 5, 6. Now there is nothing sacrosanct about this 6. If you want 7, you can put it. It is just one example that we have taken to work and understand. Okay, and all these images are from the same Stanford site that we just CS231 site, which we have looked at. All the images courtesy are from the same site. Okay, so this is how we obtain a convolutional neural network. Okay, so now let's look at implementing them. Now the first CNN network that actually came with MNIST data is by Jan LeCun. So he is the one who came up with the first convolutional neural network. So you might have heard him in recent news now, wherein which he got the highest seed money for his company in Europe. Okay, so he was earlier with Meta Labs. Now he has his own startup. So now the first CNN network that we have, this is from Wikipedia. Now this is LeNet. Okay, now this was done for MNIST dataset. Okay. Now the second column is AlexNet. We'll come to that. The first one is LeNet. Now it is the MNIST is the data. So MNIST is 2828.1. That is the size, and then you pass that through a convolutional operation, wherein which you have a 5 cross 5 kernel. Okay. So now, as you know, what are the parameters that you need to fix the thing? Now, one is the number of filters you need, the spatial extent, stride, and padding. See, whenever stride and padding is not explicitly specified, now we consider stride as 1 and padding as 0. That means that there is no padding. Okay. Now, whenever the stride and padding information is not given, stride is considered as 1 and you don't have any padding. That is exactly the case here. Now you don't have a stride. You don't have a padding. You have stride as 1. You have 2 padding. Sorry. So you have 2 padding here. So the stride is 1 now, and the size is the size of this filter, which is F, is 5 cross 5. And what is K? How many number of filters are there? That is not specified. But from the equation, we already know that. So K is D out. Now, if I know the output dimension, those many filters are there. Here they have specified the output dimension. Okay. Therefore, it is the 6 is the number of filters. Now you have the kernel size, you have the number of filters, you have the padding, and then you have the stride. Now you can obtain the output size dimension, and after that you are using a sigmoid activation, followed by pooling layer with 2 cross 2 average kernel. Now we looked at 2 cross 2 max kernel, and then you just, rather than taking the maximum value, you take the average value. Okay. and then the stride is 2. Now, as I told you, there will be no reduction in the number of dimension, but the spatial reduction is by half. So 28 becomes 14. Now, and then again, that is passed through a convolution layer, now which is having 5 cross 5 kernel, no padding. Okay, now P is 0, stride is 1, and the number of filters are 16. So after application, this is the size that you get, that you pass through a sigmoid activation, and then you pass it through a average pooling layer with 2 cross 2, and then the stride is 2, because of which spatially the dimension will be halved. So you have 5 cross 5 cross 16. Now 5 cross 5 cross 16, this you flatten it up. Now when you flatten it up, you get 400, and then you should have an MLP now to convert it into 10 number of classes, right? Okay. Now 400 to 120, so then sigmoid, 120 to 84, again a sigmoid, 84 to 10. Okay. Now why did they come up with 120, 84, 10? See, these are all heuristic numbers. Now you can come up with any numbers. They have these many fully connected layers. Now this is LeNet. Okay. Now we have to specify all of these in our code. So now let's see how to do it. So we have the code ready with us. I'm assuming that all of you are comfortable with the ideas of data loaders, the transforms, and then obtaining the data. We're using the MNIST data. Okay. So these are the necessary libraries. Torch is the base library. NN is for neural networks. This is for optimizer. This is for dataset and transform. This is for data loader. Now, if the data is there, I'll just change the runtime to T4 GPU for us to work. Okay. The CUDA device. If the CUDA is available, now then if the GPU is available, I'll taking it. Now, batch size, I'll make it as 128. These are the hyperparameters. So learning rate is 10 to the power of minus 3, and the number of epochs, I'm training it for 5. And then the transformation on the features that you're having is you're just converting it to tensors, you're not doing anything else. So this we know. How do you obtain the data set? Obtain the data loaders, that is also fine. So now comes the important thing, which is you want to convert it into a so you have to have the network structure. This is a LeNet structure. So I have number of classes is 10. Now, whenever you have a network, now we have this. Now till this point, now this is what is known as the feature extractor. Okay, and this is what is known as the fully connected layer, which is there, is known as the classification head. See, just because we are using a convolution layer, that doesn't mean that we are going ahead with classification itself. Now, if you remember one of the cases of image captioning, now you pass the image through the convolution layers, you get an embedding here, then you can use it as an input to any of these sequence models, and then you can generate the caption for it. Okay. Now this embedding which is there, now it can be used for any downstream task. Okay. It is not like you have to use it only for classification. Now this can be used for any downstream task. Okay, that's perfectly fine. Okay. So but here we are using it for classification. So that means that there is a classification head, now, which is an MLP. Now the first one is the feature extractor. NN.sequential. Now by now you know what is NN.sequential. So, and then now comes how do you define a convolution layer? Okay, to define a convolution layer, if you remember, now what are the things that we need? Now we need number of filters, the size of each filter, stride, padding. Correct. So and then if you number of filters is fine, so you can say that okay, I have 2 filters, that is fine. Now how many components should be there in each of the filters? Now that is dependent how many input channels are there. No, that also needs to be defined. From a programmatic perspective, you have to define these matrices. How many matrices of what size I have to define, and how do you define the operation? See, the operation is defined by the stride, and the input is what do you call, blown up by padding. But if you want to define the weights, now you should know how many matrices I have to define. Now in one filter, I have to define three matrices. Now, why is this three coming? This three is coming from the number of channels that are there in the input image. Okay. Now, therefore, we have to specify the number of input channels. Okay. Now, therefore, you are specifying the input channel. Now, output channel is 6. Now, output channel is nothing but the number of filters. Now, kernel size is 5. Okay. You're specifying the kernel size. Okay. So now, as of now, you have specified these two. Okay. And stride and padding you haven't specified. Now, as I told you, if stride is not specified, it is considered as 1. Padding is not specified, it is considered as 0. Now, this is the first convolutional operation. Now, after that, you are passing it through nn.relu. Then an average pooling, nn.average pool 2D. Okay, this is the 2D average pooling. Kernel size is 2, stride is 2. See, the standard LeNet actually uses sigmoid. That's fine. So we know we have passed sigmoid, and then we know that ReLU gives better values. Better, it is good in case of empirically. We know that it is good for the sake of images. Okay. And then you have this average 2D kernel, in which you are specifying it like this. Okay. And then we have another convolution layer, in which 6 is the input channel. Now, and then please remember, this output should match the input. Now, because now this is one pipeline. Okay, one is to another. Okay, and then the output channel is 16. Kernel size is 5. So we know this. And then now this is followed by again an average pooling. Now the output size here is 1644. Now then this 1644, you have to flatten it out. Now that is the reason why you have nn.flatten. Now we know in how nn.flatten works, the raster scan. And then 1644 to 120, ReLU, 120 to 84, ReLU, 84 to number of classes, which is 10. Now this we know. Now this is similar to defining any standard MLP. So this is what is important. Okay. Now input channels, to say that how many components should be there in each filter, number of filters. Now what should be the kernel size? What should be the size of, what is the spatial extent of each of the filter? Now striding and pad also you can specify if you need. And then followed by an activation, followed by a pooling layer, followed by convolution. And then, as I told you, this output channel should match this output channel. Now, because your average pooling is not changing your, number of components. It's changing the spatial dimension of each component. The number of components still remains the same. So, and then the input, same. So, the same story continues. Now, you can pitch in how much ever kinds of convolution layers that you want. To an extent, I'll tell you there is a small caveat over there. Okay. Now then you write the forward method. Now first you get an input. First you get the features. That means that this is passing it through this particular code. Okay. And then whatever is the output, that you are passing it through the classifier. This is the classifier head, and this is the feature extractor. Okay. You create an instance of the model, use the cross entropy loss, because since we are dealing with a classification problem, and then the optimizer you're using Adam, and then train epoch and all those things is exactly the same story that we did in our earlier tutorial. Then you run it for some time. Okay. Now, as you can see now, the only thing that is changing is the model. Every other story remains the same, the training and everything. Okay. Now let's run this and see how the output comes. Okay. Yeah, it is taking some time to create an instance. Now, meanwhile, let's look at another important network, which is AlexNet. So to understand AlexNet, we should understand a very important data set, which is known as the ImageNet. Okay. Now, this ImageNet is a 1000 class problem. Okay. That's ImageNet. Okay. So the ImageNet is a 1K classification. That means that you have 1K classes. Okay. So now what they did was they came up with a computation for this, saying that whichever we will give you the training data and then we withheld the test data. So, and then you have to give your model. We will run the test data. Whoever gets the highest accuracy, that is considered as the winner. Okay. Now, one of such winners is actually known as AlexNet. Okay. Now, the size of each image in this ImageNet is 224, 224, 3. It is resized to this. That is the reason most of our input for, let it be AlexNet, and the next network that we'll be looking at is another network called as VGG, or the next network that we'll be looking, which is another network called as ResNet. Now, all of them has this structure, which is the input 224, 224 cross 3, which is because of it has come from the ImageNet family of development. So that you pass through a convolution layer, which is 11 cross 11 kernel, stride is 4. So number of filters is 96. There's no padding. And then you pass through the ReLU activation. And then you see here, it's not always mandatory that you should have 2 cross 2 kernels for pooling. Now here you have a 3 cross 3 kernel and then the stride is 2. We use the same formula, which is Hn minus F plus 2p divided by S plus 1 to compute the thing. Okay. Now, so on and so forth. Now you can see here that how it is going ahead. Okay. And then we know the idea of dropout. Okay. So in a network, now randomly you make 50%. This is 0.5. Now randomly you make 50% of the weights as 0. Okay. And we know that any kind of restriction on the weight can be thought of as a regularizer. And this is a regularizer that is there to avoid the idea, the problem of overfitting. Okay. Now this is the AlexNet. And then as you can see here, the output will be it's a vector of 1000 values. It's a probability vector of 1000 values. Okay. After passing it through a softmax. Now, normally we don't use the softmax. We normally get the logits. Okay. And then the loss will take care of converting that to the softmax. Okay. Now this is the whole story of AlexNet. So I'll leave this as an exercise. So since you're able to understand and implement LeNet, it is just an extension of it. The AlexNet, in which you have much more number of layers. But one thing is getting an ImageNet and running it is a bit difficult. So you can take a 224, 224 cross 3 random matrix and see whether the matrix operations that are there here is actually matching the size. Okay, so you get the output. So let's see the output of our LeNet. Yeah, it has done. See, we got 97.95 as the train accuracy and 97.94 as the test accuracy. So within the 5 epochs that we have done. Okay. Now this is how you come up with the any CNN architecture. So now in the next tutorial, now what we will do is, now we will look at a couple of important architectures like VGG and ResNet, and how do you implement them, take the pre-trained values. So for a 1000 class problem, if you are not dealing with a 1000 class problem, how do you change it for how many number of classes you have? And then how do you go ahead with the idea of feature extraction in these larger networks? And then the idea of normalization we will look at in the next part of the tutorial. Thank you. I hope you learned CNNs.